So another major machine for DC motor or for motor lecture will be brushless DC motor. So these are kind of extension for conventional DC motor. So later on, we can see how the motor work and why there's so much attention from there. Of course, mainly about the brushless. We don't need to use the slip ring. We don't need to use commutator. So that's why the motor will be much more convenient, less maintenance, probably no maintenance. We don't need to change the carbon brush too. So that's why this motor has been used in many applications, including in some cooling system. You see many of your computer, the cooling fans, they're using brushless DC because firstly, the speed will be really, really high. The cooling fan speed can be several thousand RPM, maybe 10,000 RPM. To do this one, we must go for the brushless DC. You see, when you're using carbon brush, there's a contact point, so you can't have really high speed anyway. Usually, but for brushless with commutator machine, use 1,000 RPM, 2,000, 3,000 a maximum. But if you go for 10,000, you have problem. You can't use carbon brush because there's a lot of the contact point there. You create a lot of friction. The motor cannot rotate too fast. But for brushless DC, we mainly tend to go for high performance system. We don't like to have maintenance. So that means for all the computer you use, computer fans you use nowadays, they all brushless DC. The circuit inside look very complicated, but however, today when we have fabrication technique, we're able to fabricate all the sensor, all the component, all the machine inside a really small compartment. So in this case, brushless DC still quite low cost and also easy to control too. So in here, we tend to show you the basic configuration for brushless DC. And then next lecture, we're going to show you more about the control method. So the target question will be, firstly, if you do have a conventional DC motor, how are we going to change it into brushless? Would there be any possible you can do that? Just you think you've been working with DC motor for lecture and also for your hardware right in the lab. Can you think of some skill how to change them without the brush, without the commutator? How to do that? For the brushless DC motor will be either change the current, right? The commutator is mainly to when you go 180 degrees to change the current direction, so they continue with the top become single rotation. So that's the key thing to do that. So now the question is, how do we do that brushless?
Imagine some sort of like mechanical ball bearing system. Like, isn't like a probably be like a mechanical thing.
Yeah, that's what we have been doing using commutator and compress to create a mechanical link so that we're able to change the current. But nowadays we don't like to use mechanical interfacing. We tend to use pure electronic. Everything becomes electronic control, right? So that's how we become our double E. Double E mainly try to eliminate all the mechanical, except all the electrical. Yeah, so that's how we try to do here. So even though vehicle, we eliminate all the components for vehicle. So for my electric vehicle, we don't have any, so all the braking system, annual braking system, all pure electric. The motor wheel, we don't have sharp gearbox, clutch, and transmission. We use direct drive to connect the motor to the wheel directly without any component in between. Even though the suspension in the past, we had hydraulic, electrohydraulic, or spring. But now we use all electric suspension. So today, all the electric vehicles have no mechanical part. So that's how we make the lifetime for vehicle become much longer, low maintenance. Any with mechanical part, they have maintenance. So now they can see that one thing they do is eliminate all the mechanical part from the DC motor into brushless. So later I'll show you how we're going to do that. And then how we're going to change the current for the winding. To change the current winding using commutator. Of course, as we say, we use power electronic to change the current because turn on and turn off bias switch. We can connect the winding to the top rail or bottom rail to change the polarity. So that's the way we're going to do. But it's going to show you how to do the application of brushless motor. Of course, any motor we like to have high speed 10,000 RPM or no maintenance, then you can use the brushless DC motor. So the market share getting much higher nowadays, much higher than the brushed DC motor. We tend not to use the brushed DC motor. But however, in your home, you still can see some of your power drill using brushed motor. If you buy a power drill, sometimes they come with some carbon brush for your replacement after a few months. So that is the brushed DC motor. But for those high performance, then they tend to use brushless. So today we're going to show you the basic topology, how the motor look like. And we also have an equivalent circuitry to show how to relay this motor into a circuit method to understand the operation. And we also show you the characteristic. So since the characteristic or the circuitry are quite similar to the conventional DC motor, so that means this chapter is really simple, very similar to the conventional DC motor. So I don't think you have any problem. We go through some tutorial to show you the operation. So firstly, let's see the brushed DC motor is a really conventional method of the rotation. So we have been working on this motor for many years now. I mean, for instance, I think the first one of the motor we developed is also the brushed DC motor. This is conventional method. And then, but however, this motor need to integrate a lot of mechanical interfacing, including the armature need to handle armature, the armature need to handle with the mechanical current, and also need to provide with the magnetic flux. So that means all this bottom work, we do need to have a lot of mechanical interfacing for the carbon brush and also commutator. So because of this one, we do have friction, wearing, and spark, which we don't quite like. So for some high performance system, the contact point create a spark. So that means this motor cannot be used in some application, like if you want to use in the mining, then machine, we don't like that because in mining, then there will be some sort of the dangerous gas. So we can't do that. And also in some location, if you do have some emission, gas emission, we cannot use that too. So that means other shortcoming mainly about the mechanical disadvantages. Once we had any friction in the carbon brush, commutator, it cannot be any high performance motor anyway. So the friction there, the carbon brush, and the contact point all become the shortcoming for this kind of motor. So, but the new method we do here, not new method, we have been using this motor for quite some time. So now that we turn the motor inside out, the thing is, conventional DC motor, the winding are connected through the stator, and then through the carbon brush, connect to the rotor. So then the rotor is now rotating with the winding. The winding is rotating, you need to connect it, you need to use carbon brush and commutator to do that. So however, instead the winding is inside the central, but we turn it inside out, the winding is now become external. Put the winding in the stator and put the PM permanent in the rotor. That means you put the motor inside out. So that's a possible thing. We don't need to worry about the winding connection. The winding connection always connect to the external power source. So we don't need to worry about when the motor is rotating, how we provide power to the winding. So that means we turn the motor inside out, we are able to solve the commutator and carbon brush problem. The second question will be how we change the current. To change the current direction, we just use power electronic to do that. So that means using power electronic and put the motor inside out, then we're able to change this motor into brushless DC motor. So that means you can see that so that means if anything winding here, we can therefore connect directly to our wiring connection, always support current to each of the winding, and then that will become our stator. We don't need to use the winding in the rotor. But one thing you can see that will be, if you want to power up the winding in such a way, you need to detect the motor position. The thing is, the winding need to match up with the position of the permanent magnet inside. With the winding, when energized in the lock pole, you need to against the lock pole of the PM inside the rotor. So that means when the motor rotates a certain position, you need to ensure that when you energize it, you're able to create a magnetic force. So that means you need to determine the position for the rotor. So that will say you need to have some sensor to set the position of the rotor, and then you can, when the rotor PM rotate a certain location, you energize the corresponding winding. So that means you do need to have sensor. So this sensor uses a Hall effect sensor to detect position, detect the magnetic field inside the rotor. And then the commutator now using electronic commutator. So that's to say we need to use power electronic to control the motor current. So the inverter will be doing one of the job in order to have the synchronization together with the magnetic field produced from the rotor. So to do this one, then later on we can see some circuitry. You can see how it actually look like. So that means you can see that the conventional DC motor, we use automatic switching using a commutator. But now then we use power electronics to do the switch. For brushless DC motor, the PM now fix the rotor. But for conventional DC motor, the PM will fix in the stator. So that's how the difference between these two. And the brushless DC motor, the winding becomes stationary. Like in here, the winding becomes stationary, don't need to rotate. Once the winding have no rotation, then the wiring connection will be much easy and simple. So now then, that's how the connection look like. So firstly, we got a set of winding in the stator. So outside is our stator. Then we have three kind of the winding for instance, that's a three-phase brushless DC motor. So we got alpha phase here, yellow phase, and blue phase, represent three phase. Each of phase winding here are connect to each one of the phase of the inverter. So that means you can see that for this point here, if you turn on the top transistor, this polarity becomes positive. If you turn off the top transistor, turn on the bottom transistor, this polarity becomes negative. So you can actually control the polarity of this connection. So that means we can able to control the current go into each of the winding. So that's something we can work on. So each winding, so the motor inside actually have three set of the winding, like the three phase. Then each winding we can control them properly. So three phase here, usually each of phase will be displayed by 120 degrees. So that means these three phase are controlled by the three inverter leg. Each one will also turn on by their own 120-degree displacement. So you can see that we have two PM in here, a PM north pole and south pole. So for instance, this, when the rotate to here, then we can turn on this winding so that these two have an opposition to force the motor to rotate. So that means we need to detect the positioning for the PM in the rotor. So we put a Hall effect sensor or other sensor to detect the position where the rotor rotate to. So that's why in here, this one of the main disadvantage for this motor will be we need to detect the position. So without a position sensor, the motor doesn't work. So that is to say the connection of this motor have more connection. Firstly, we have a three-phase connection to the motor winding. We also need to have position sensor to sense the location for the rotor. And then this will provide us which transistor we're going to fire. Then let's see the waveform. So that's how the waveform look like. So each of time will energize one of the phase of the winding. So you can see that if we using the transistor, we can turn on one of the phase. Then once we excite them, like apply the EMF to the winding, then we are able to create the motor current in that particular winding. Then you can able to induce the EMF in the winding like the conventional motor equation. When you apply the DC voltage there, then we have the losses due to the winding resistance plus we have the back EMF produced. So you can see that for each, we have 3 phases in here. Each of the phase, we're going to energize the winding with certain current. So this current profile is controlled by us by using our inverter. Each time when we turn on, we inject the I current here, say the IR current here, to produce a square wave current like this. The turn on time here will be equal to here, will be 120 degree. Each time we have 120 degree for red phase, and then another 120 degree for yellow phase, and 120 degree for the blue phase. So in that kind of the sequence, we can anytime we can energize the winding. But each time in here we'll have 2 winding conducting the current. So in here, if the red phase conducting, then the return path of the current will go through another winding. Like in here, will return through the yellow winding. And the next, then we can switch to the blue phase, then return path in here, go into red phase, return from the blue phase. So each time we have to do that. So because the motor, for instance, for this example, we are using star connection. So if we got the winding here, for instance, that is red, yellow, and blue. So when we energize them, so that will connect to our inverter, right? A power electronic inverter. So when we inject to here, go through port, and then we can turn on the corresponding transistor here to determine the current go through here or the current go through here, right? So then each time there must be at least 2 winding are conducting. So that's to say, for instance, in here, the red phase go to here and then return through the yellow phase. So that means it return to here. Okay. So that's how the basic operation, how we demand which winding to operate. So at least 2 winding are conducting, and then how to conduct these 2 winding depend on how we turn on the transistor. For instance, in here, if you want to do that, if that's the red phase, yeah, the red phase will go in here, and then it come back from the yellow phase, yeah. You can connect here. So that's how we make the current operate. So that internally, inside here will be just our 3 phase, right? 3 phase winding. So that's how the basic operation for this motor. Any question up to this point? So you can see that in here, we combining with the power electronic to switch the current in 120-degree manner for each of the phase. And then we can therefore control the current direction. From there, we can able to make it behave exactly the same as a DC motor. So you can see that if the current go in here and come back here, so inside here, there must be full 2 winding. So each time we have 2 winding being excitation. These 2 winding, they have their own armature current, and the current will pass through their RA, the armature resistance, plus they also have their own back EMF. So that's how they look like. So that means later on you can see that we do have, once the current passes through the winding, we have the back EMF. So that's why you can see once we have current here, we have back EMF in here. And then that's the back EMF. But you see that the back EMF waveform is more look like horizontal. So you can see that the horizontal BMF. Later on, I'll explain to you why there will be horizontal back EMF. Because imaginally you can see that if we have a current here, we only have this part of the back EMF. Once we have current pass through, we have back EMF. But we actually can see that back EMF have a kind of horizontal movement from negative to positive and positive to negative. Later on, we'll explain why it looks like this. But bear in mind, you can see that the back EMF from the winding will more look like a horizontal kind of the back EMF coming out from there. And also the back EMF are all displayed by 120 degree. So which you can see here, we got 120 degree in here, that way another 120 degree, and then you try to stop for 60 degree, stop for this 60 degree. That's how the pattern look like, how the driving pattern look like. Because three phase anyway, so each winding should conduct for 120 degree. So this kind of waveform, we call them the quasi square waveform because they are not really complete square. They are quasi. They are not real kind of the waveform. And again, we are energize them for 120. So in the 120, then when we have a positive current goes into here, then the back EMF also become positive, which is the same when we have the motoring operation for conventional DC motor. So this part will exactly the same as what we understand for conventional DC motor. And this part is the reverse part because there's a return path for the red phase. So for instance, in here, you can see that let me get an eraser then, or I can change the current. Station. I can't change it. Anyway, so we turn on this one by using 120 degree. This, and then, but however, we can also conduct other phase. For instance, when we operate on, so when it becomes negative here, so that is to say we can conduct the yellow phase positive and red phase negative. So under that phenomenon, how the circuit look like? So that means the yellow phase, for this yellow phase, if we turn on this one, let me change the color to blue, right? So if we turn on the yellow phase here, then that will become positive, go into yellow phase, and then come back from here, become negative. So we can control the switching here to control which winding is positive, which winding is negative. So that is to say we are able to create the waveform to become negative in this case. So that is to say we here, by using the switching, we are able to control the back EMF or current is positive or negative. But the pattern will be basically using this pattern to control each of the phase. Up to this point, do we have any question? You need to think about how the current flowing in the three-phase motor and also the three-phase inverter. And then from there, you can try to match up this diagram to the circuit diagram. So mainly about how the current flow go inside the winding, can go outside the winding. From there, you can therefore relate to this diagram. You need to have some time to digest how the correlation between them. So next is try to explain to you why we have horizontal. So this is straightforward because when we have positive current, we have positive back EMF. When we reverse everything, reverse the current pattern, opposite, then that means the current becomes reversed, the back EMF also reverse. So that is two understandable. And then
I'm a little confused on how the torque is developed to rotate.
so say the torque reverse.
Yeah, like how does it rotate? So we have the coils going around, it's like current, and so it's gonna go.
You want to relate to the Lorentz force, right? How
Yeah.
the force being developed. We did not written down a diagram here how to relate them into Lorentz force. But I did not tell you about the positioning for the winding here. But bear in mind, we got the, say, for example, north and south pole here. And then when we energize any particular winding, we tend to create an opposite force. So this winding, this current here, pass through this winding, together with the magnetic field here, then we need to position the current through the winding in here, together with the PN parallel magnetic inclined rotor to create a Lorentz force. So that means we must position the winding to be 90 degrees with the magnetic field inside the rotor. In here, I did not show you how the winding looks like, but you can see that we're going to put the winding here. So the magnetic field will go in vertical. And then our current winding here must be go through in this direction, so that these two can be able to create a 90 angle between them. That's how we develop the force. The thing is, this diagram is more complicated. It's difficult to draw each of the phase to do. Conventional this model simple, just join one loop, then you're able to imagine how the force look like. But here, when we have three phase, then you have to think about how we arrange each of winding and able to create you with the rotational force. With a vertical field, the field is now vertical. And how the position of the winding shall be the I current direction to create you vertical force. You try to rearrange your winding to see how you're able to do that. So you can see if the field going in this way, you're able to make the current go through this way, the force will go this way. So that means your winding must be go through the paper in order to create your vertical force.
So on go back to the real life image. No, not the diagram, but the deconstructed picture on previous slide.
I don't have that diagram here, but there's a multiple diagram in the system. Yeah, you can see in this diagram. Yeah.
So where's the north pole behind it?
Now you can see this from this diagram, the winding, the state winding will be here. So the current will be this way, right? The vertical force will be this way. So that's why I can create the vertical force in this time. That's what. Okay. Good. So you can see that this is the current. The magnetic field will go this way. So that's why the force will go this way. So that's why I can create the rotation. We need to have some kind of the imagination. Right. Good. To do that. So that means you have this way is the current, and then you have this is vertical force, right? So that's why you can create the force in the plane in this direction, right? So when we have a multiple phase, then each phase will provide its own magnetic force. But of course, this is a more number of phases, this diagram. But the illustration here, we're only using 3 phase to make it easier for you to understand the operation. The real application for simple motor usually about 3 phase. But for high performance motor, we tend to use multiple phase. So that means here will be 3 phase. But when you go for multiple phases, then you also need to use multiple phases. So now then, let's go through why the magnetic field, the back EMF will change direction. So when we have so the rotor here will continue to rotate anyway. So when you so that means when we rotate to here, then that means you therefore this field, magnetic field will probably say you go up here, then interact with the winding, create to you with the back EMF in this particular winding. And then you can see that the north pole will rotate in this direction, for instance, and then you'll be replaced by the south pole. So in this case, once you go to south pole, then that means the polarity will be changed. So that means you can see that the back EMF will also be changed, right? And then when we change between north and south, between them, they're not instant. You can see there's a gap in here. They're not going to change instantly. They change gradually from north to south within this gap of 60 degrees. So that's why I can see that the back EMF in here will move at the end of the north pole. When you change to south pole, this will be gradually move from the magnetic field from north to south in this changing manner. So that's why I can see that the back EMF will therefore move from the positive to negative because it represents how the magnetic field changes from north to south pole. That's how it looks like. Of course, in here, I draw it in linear manner, but actually they may not be linear. They may have some curvature, maybe the curve will more look like this, depend on the configuration of the motor. But here, it mainly to show you the PM will vary. The PM field interact with the winding will be varying. Depend on the configuration for the PM inside here. So the PM usually cover 120 degree and also 120 degree here with empty 60 degree to avoid the isolation between the two fields. And then therefore you end up with the back EMF changing between the north and south pole. So that's how we understand why the back EMF look like this. I think you did do the lab section. You can see something similar like that. But of course, this would be more theoretical back EMF. But you can tell me more about when you do the experiment, how the back EMF, how the current look like. So you can see that if you use current mode control, we inject current into here, make the DC current, and then we have a reverse DC current here. But now then you can also tell me how the particle motor look like, how the current waveform should look like. Already over the time. So we stop here, then we will continue next week about how we understand more about the DC motor, how the equivalent circuitry look like, how we control them. Okay, see you again next week then. Bye for now.